Welcome back to Physics 141 online. I'd like to extend our treatment of one-dimensional motion to deal with a special case where we have objects moving vertically up or down near the Earth's surface under a special kind of constant acceleration motion. But first, let's review the equations that we worked out last time for the relationship between velocity, acceleration, and position for an object moving in constant acceleration motion in one direction. The first two equations came from our graphical understanding of the velocity versus time graph, which is linear when you have constant acceleration motion. Then, various ways of combining these two equations give us number 3, number 4, and number 5. Each of these equations is unique because each of them is missing one of the 4 kinematic quantities that we've defined so far. Notice that we've got position x, we've got velocity, we've got acceleration, and we've got time. And all these equations have one of those things that's been eliminated from it. For example, equation number 3 does not have time. Right? Equation number 4 does not have acceleration. And equation number 5 does not have v0, the initial velocity. So they can be useful for certain kinds of problems depending on what kind of information is given to us. And you'll just have to get some practice working with different kinds of problems, identifying the given quantities, the unknown quantity, and then figuring out which equation to use. Now, our next section then deals with this condition that our book calls vertical free fall near the Earth's surface. It's a fact of experiment that when an object is thrown straight up in the air or it's released and falls down to the Earth, that it accelerates in a constant fashion with a constant acceleration that is toward the Earth. So whether an object is thrown upward or whether it's released and falls downward, it doesn't matter what the direction of the motion is. The acceleration is always equal to a negative constant, the minus sign meaning that the acceleration is downward. Now how does that make sense? If the object is moving upward and we throw something directly up, its speed decreases. And that's represented by having a negative acceleration, right? If, on the other hand, we release something from a certain height and it falls downward, its speed increases, but remember it's in the negative direction. And that's the same thing as having a negative acceleration. So this minus sign is important, and we usually pick a symbol, lowercase g, to represent the numerical value of this acceleration. So g on Earth is 9.81 meters per second squared. This quantity actually varies slightly depending on where you are on the Earth, but it's very close to this value overall. Notice, however, that g is just the number 9.81 meters per second squared. The minus sign still has to be supplied because the acceleration is indeed minus that value. Okay? So all we're going to do with our 5 kinematic equations is show how when we substitute a equals minus g, we get a special case of each of these that applies to conditions of vertical free fall motion. So the first equation is easy. A is equal to minus g, so we get v equals v0 minus gt. The second equation, we only have one substitution to make, so a becomes negative g, and you see the resulting equation on the right. The third equation, the same thing. A is equal to minus g. This one is notable, again, because it's the one equation of the 5 that does not contain the time variable. So it can be useful if we have some given quantities, but we're not given any information about the time. The fourth equation doesn't have any change at all, right? Because the fourth equation did not have acceleration inside of it, so the equation's the same. And the fifth equation becomes now x minus x0 is vt plus a half gt squared. So what we then have, these are not new equations. They're simply the special cases for the original equations for motion vertically up and down near the Earth's surface. And in order to illustrate how we use these, we need to work out an example problem. And this example problem actually comes from your textbook. It's Wolfson Chapter 2, Exercise 214. And I'll just explain it for a second and then show you at least an approach to working out the solution. You'll have this problem for homework, but it'll be a numerical problem, and each of you will be given a different numerical value for the initial speed. So everybody will get a different numerical answer, but since you're all going to work the problem out symbolically first anyway, then the solution will begin with the same steps for everyone. So here's the problem. If you're a baseball fan, this will be a familiar situation. Batter swings at a pitched ball and he hits it directly upward. So the baseball leaves the baseball bat going straight upward at a speed v0. And that number will be provided. So all we know is the ball goes straight up and we know its initial speed. The questions are, how high does it go? What's its maximum height? And then how long is it in the air? And what we mean when we ask how long in this problem is, for what time is it in the air? It's going to ascend to a maximum height, fall back down to where it came from, and what would be the total time elapsed. Alright, here I have the same problem set up in a different format so that I can use a stylus to show how to set this problem up and work toward a solution. Ultimately, you'll have to finish that by using the appropriate numbers that you'll get when you open this homework problem up through the Mastering Physics website. So what are we going to do first? Remember again the whole process of problem solving using the IDEA method. I is to identify what type of problem it is and what information is given. D is to develop a solution strategy. E to evaluate the results. And then A is to assess and see if they make sense. So we'll generally follow this same process here. We read the problem and we realize it's a one-dimensional motion problem. Since it's presumably happening on Earth, it's constant acceleration motion. So that's what we have, constant A. And since the ball is hit straight up in the air and will therefore come straight back down, it's one-dimensional motion. Okay? D, develop a solution. We now are going to have to look at our toolbox of equations and see which one to use. But in order to do that, we actually have to finish the identification step and ask what's given. First, though, I'll draw a sketch. This sketch is a very simple one, maybe a little oversimplified, and here's where the ball is hit from right down here near the Earth's surface. It goes straight upward with an initial speed v0, and I will use a dotted line to indicate the trajectory as it goes up, because eventually it's going to reach a maximum height and then come down again. And of course it will come straight back down if it's truly one-dimensional motion, but I've displaced my sketch a little bit just to show that indeed it does come back down. And a piece of given information here that's easy to overlook is that we know something about its motion at the very top, at its maximum height, because we know in order for it to turn around, the velocity at that maximum point has to be 0. It has to stop for just an instant at the top. Now this does not affect its acceleration. The acceleration is the same all throughout the motion. The acceleration will always be, all throughout, be equal to negative g, which is negative 9.1 meters per second squared. Okay? That does not change. All throughout the motion, acceleration is the same. But the velocity initially is v0. It slows down as it reaches the top. Then it reaches 0 for an instant and turns around and becomes negative. So on the way back down, the velocity is negative, because even though I haven't indicated it, I've been assuming that the x direction will be positive upward. Okay, that's my coordinate system in this problem. And so those are the quantities that are given to me. What I'm trying to find, right, is I'm actually trying to find delta x, from the original spot to the maximum height. So that's x minus x0, or, as I've indicated in the problem, delta x. That's what we're trying to find. So we've really pretty much completed the identification step. We've identified given quantities, and now we know what we want to find. So which equation is the one that we should use? We have these 5 kinematic equations, and the big clue here, sometimes we won't be able to answer this question right away, but the big clue here is no time information is given. At least as far as the problem is stated up till part A, no time information is given. And so because of that, that suggests that we use the equation v squared equals v0 squared, right? And in this case, it's minus 2g times x minus x0. That's the equation that was the third equation in our list of kinematic equations. So let's see, will this one work? We're trying to solve for x minus x0, or just delta x. I'll call it that. That's the height that the ball reaches. We know g, we know v0, and we know v. Right? All these quantities are in our list of given information. Even though no numbers are provided, the fact that we are told that the fall ball starts with a velocity v0, it means that that's a given quantity. Your problem actually will have a number associated with that when you work it out. So v0 is a given quantity. G is given, and then v, the final velocity at the top, that's also given. So this equation should work. Let's now substitute for the quantities that we know. In this case, we know that v is equal to 0, right? So we have 0, and I'm just going to still write this as v0 squared because I don't have a number. And then we've got minus 2g delta x. And so now, before plugging any numbers in, we want to solve for delta x, which is easy to do in this equation. We add 2g delta x to both sides. So we get 2g delta x equals v0 squared. Divide both sides by 2g, and here's where we basically get our answer. Delta x is v0 squared over 2g. All right. Of course, this is not a final numerical solution, but it basically, in principle, is as far as we can go. If you know that v0 is 10 meters per second, then you can plug that in and get an answer for delta x. So I will skip the assess step. We basically have gone through the identification, the develop a solution. That was the question of finding the equation to use. E was evaluate. We did that already as well. Assess would come after we find a numerical value. All right, so that's part A. Now part B, how long is it in the air? What's the time? All right, so part B, all the given information is the same as what we have above, but now the quantity we're trying to solve for is t. Which one should we use? Well, we've got several choices, and it might be a good idea right now for you to stop the video, pause it, scroll back a few seconds to look at the list of equations that was provided on my PowerPoint presentation and figure out which one you should use to solve for time. So go ahead and do that. All right, now I assume that you have looked at the equations and you have some idea. There actually is more than one approach that would allow you to solve for time, but I would maintain that the simplest equation, making use of the given information and solving for time, would be the equation that says v equals v0 minus gt. The reason is we know g, we know v, we know v0, and we'll solve for time. So you'll see how easy this is. V, of course, at the top is equal to 0, right? v0 we know is just v0, all right, minus gt. So if I then add gt to both sides of the equation, I get gt equals v0, and solving for t, I get v0 over g. All right, so this is the time that it takes the ball to go from the initial location to its maximum height. So this is, I'll just write that down, time to max height. So I've calculated that correctly. If I knew the value for v0, I could actually get a number for it. But if I go back and look at the question one more time, it's actually asking something a little different. It says, how long is it in the air? So the ball hit from the ground goes up to a maximum height and then comes back down all the way to the ground. So the time it's in the air, because this problem is symmetrical, we're assuming there's no air resistance at all, the time it's in the air will actually be twice this time, right? So, but v0 to v0 over g equals the time in the air. And that's a subtle point. It's easy to miss that, but if I read the question carefully, I think it's pretty clear that that's what the author is asking for. Okay? So we solve for the time to go to the maximum height because that was the final location where the velocity goes to 0 at the very top. But if we want the total time in the air, we double that result, and that's the answer. So I hope this is helpful. You should now be able to look at several other homework problems that make use of these equations for vertical free fall problems with constant acceleration motion and apply our 5 equations for kinematics to be able to attempt solutions to those problems.